Alright, as promised, I have a resistor circuit problem for you guys. You can already see the setup here. We have a 12-volt battery connected to 6 different resistors with different resistances, and we want to find the current through and voltage across each of these resistors. To do so, the first step in any of these problems is to find the equivalent resistance and then use that to find the current through the battery. So that's where we're going to start. So the first thing you need to do to find the equivalent resistance is look for any two resistors that you can say for sure are in series or are in parallel. So a lot of people want to jump to R1 and R3 up here. So resistors are only in series if all of the current that flows through one has to also flow through the other one. So current can flow through resistor 1 here, but then there's a junction. So some of that current will go through R3, but not all of it, so we can't combine those yet. However, we do have one set of resistors that we know for sure what arrangement they're in. R4 and R5 are in parallel with each other. The paths split right here. They come back together right here. There are two options. The current can either go through R4 or it can go through R5. And R4 and R5 are the only resistors on that path, on each path, so we can combine those. So the first thing we're going to do is combine R4 and 5 in parallel. So this will give us R4-5, as I call it, or the combined resistance of resistors 4 and 5. And using our equation for combining resistors in parallel, this will be R4 to the negative first power plus R5 to the negative first power, the whole thing, don't forget the parentheses, to the negative first power. So plugging in that 15 ohms and that 41 ohms, we get a value out of this of 11.0 ohms. And it can be helpful to redraw our circuit after each step to see what's happening. So I won't label everything, but the circuit now looks like this. Where it will take me a second to draw it here. Most of the circuit will remain the same, only the parts that we just combined will combine themselves. So over here on the right used to be R4 and R5. Now we have just R4-5, those two resistors combined into one. And let me label at least one more resistor here, R3, because our next step after this is to, again, find two resistors that we know for sure are in series or in parallel. It's too soon for anything else, but R3 and R4-5 are in series with each other. So however much current gets to R3, all of that current has no choice but to go through both R3 and R4-5. So then we want to make R3-4-5, or the combination of resistors 3, 4, and 5. We've already said this is R3 and R4-5 in series, and when we add resistors in series, we just add up the numbers, nice and easy. So this gives us a value for R3-4-5 of 22 ohms. So that's the 11 ohms from R4-5 plus the 11 ohms from R3. And again, we will redraw our circuit. So we still have the battery, and most of these resistors have not changed, so anything outside of that circle that I drew before is going to stay the same. Except now, where we used to have R3 and R45. Now we just have R345, that 22 ohm equivalent resistance of just resistors 3, 4, and 5. So maybe you can see right now, hopefully you can see right now that R2 and R345 are in parallel with each other. So R2, or to keep the same notation as earlier, 2 and 345 are in parallel with each other. So to find the combined resistance of R2 and R345, we'll call that R2345. We will use our parallel resistors formula. R2 to the negative 1 plus R345 to the negative 1, the whole thing to the negative first power. Again, don't forget those parentheses. So we're taking the 22 ohms from R345 and the 32 ohms from R2, and when we combine those together, we get 13.0 ohms, and we once again redraw our circuit. So we still have the battery, we still have that first resistor, we still have that last resistor, but now R2 and R345 have been combined together to give us R2345. Then we have R1 and R6 as well. So now we look for, again, resistors in series and parallel. And all three of these resistors are in series. So R1, R2, 3, 4, 5, and R6 are all in series with each other. So to combine things in series to get R1, 2, 3, 4, 5, 6, that's just going to be R1 plus R2, 3, 4, 5 plus R6. So adding the 20 ohms from R1 to the 13 ohms from R2345 to the 8 ohms from R6 gives us a total value for R1, 2, 3, 4, 5, 6, or since those are all of the resistors, that's the equivalent resistance. Then that gives us an equivalent resistance of 41.0 ohms. So that is our final answer here, at least for the equivalent resistance part. And from here, we would move on to finding out some things about the rest of the circuit. To do that, I'm going to have to clear myself some space here. So we have the same setup as before, and I will start with the value that we know, which is the equivalent resistance is 41.0 ohms. Now before we move any further here, I want to get a list of all of our major circuit rules in one place, so I'm going to put them up at the top right over here. What I'm going to refer to as resistor circuit rule A for the purposes of this problem is that the voltage drop is the same in parallel. So when you have two parallel paths, they must both dissipate the same voltage. Another rule that you should be familiar with is that since voltage is the currency of the circuit, all voltage you get from the battery, you must spend before you get back to the battery. So no matter what path you take through this circuit, you're going to have to spend all 12 volts that you got from the battery. General rule C that we can use for circuits is that current is the same in series. And this comes from conservation of charge, just like voltage being the same in parallel, comes from conservation of energy. Both A and B actually come from conservation of energy, just like both C and D come from conservation of charge. Current is conserved at junctions. We will see this come into play as we get to Kirchhoff's laws on Friday. And last but not least, probably our most versatile circuit tool, we have Ohm's Law. V equals I R. So I will let you know as we're using each of these throughout the course of our solution here. So once we have the equivalent resistance, I said the next step after that was to use that equivalent resistance to find the current through the battery. We do this by making use of Ohm's Law. Ohm's Law is always V equals IR, but it can refer to the entire circuit, or just a small piece of the circuit, or just an individual resistor. If we want Ohm's Law to apply to the whole circuit, we need the battery voltage, the battery current, and the equivalent resistance. So plugging in some values, we have 12 volts for our battery voltage. We don't know the current through the battery yet. And we already found our equivalent resistance of 41 ohms. And this is why we needed it, so that we can get the current through the battery, which is 0.2927 amps. So I'm going to keep quite a bit of decimal places a lot of the time so that our rounding error doesn't really start to pile up. From here, once we have the current through the battery, we have to start to use our other circuit rules, A through D. A good one to start with is C up there. Current is the same in series. And R1 and R6 are in series with the battery. So that means that whatever the current through the battery is, the current through resistor 1 and the current through resistor 6 have to be the same thing. So resistor 1 and resistor 6 both get 0.2927 amps. And now we've got the current through two of our resistors. From here, we can use Ohm's Law. So this time, we used our general circuit rules to find the current through the resistors first, and now we're going to use Ohm's Law to take that current and find the voltage across each resistor. So again, V equals IR, but we can apply Ohm's Law to a single resistor. So for resistor 1, the voltage across resistor 1 is the current through resistor 1 times the resistance of resistor 1. Or in this case, that's that 0.2927 amps times R1, which is 20 ohms, which gives us a voltage drop across resistor 1 of 5.854 volts. And we can do the same thing for resistor 6 as well. So note that it doesn't matter that R6 comes at the very end of the circuit. As soon as we know the current through it, we can use V equals IR. So V6 equals I6 R6 using Ohm's Law for just resistor 6. And we have the current through resistor 6, which we've already found out is the same as the battery current, 0.2927 amps, times the resistance of resistor 6, which is 8 ohms. And that gives us the voltage drop across resistor 6 of 2.342 volts. So we have made a good start, but once our current goes past resistor 1, then we hit a junction. and the current has to split. So we know the current will split in such a way that more current goes towards the path with less resistance, but we don't know exactly how it splits yet, so maybe it's time to pull another rule out of our pockets here. So let me just kind of wall off this section here to keep the work nice and separate. And now we'll move on to a new section of the circuit, starting up here, and we're going to make use of Resistor Rule B now, or General Circuit Rule B. You can use these for other kinds of circuits as well. B says that all voltage you get from the battery you must spend. So for B, we consider different possible paths through the circuit. One possible path we have through the circuit is this one right here that I've just outlined in blue. So whatever voltage you get from the battery, you must spend along the way. So the voltage of the battery has to equal V1 plus V2 plus V6. This is because that path through the circuit that I drew goes first through resistor 1, then through resistor 2, then through resistor 6. And this can help us here because we already know V1 and V6. So, writing this out, we have 12 volts, the voltage of the battery, equals the voltage drop across resistor 1, 5.854 volts, plus V2, our unknown, plus the voltage drop across resistor 6, which we already know, 2.342 volts. And from this, we can get V2 equals 3.804 volts. And we've got another one of our voltages squared away. Now, once again, we can pull Ohm's Law out of our pocket. This time, we found the voltage across the resistor based on our circuit rules, so then we use Ohm's Law to find the current. So just to make it clear, again, we're using V equals IR, the Ohm's Law, but just for resistor 2. So we want the voltage drop across resistor 2, the current through resistor 2, and the resistance of resistor 2. So that's 3.804 volts, that number we just found, equals I2, which we do not yet know, times the resistance of resistor 2, that 32 ohms. And this gives us the current through resistor 2, which is 0.1189 amps. And we have ourselves another value. So we split our current up here at this junction, and some of it, that 0.1189 amps, went towards resistor 2, but the rest of it must have gone the other way because Rule D, current is conserved at junctions. So the current we have coming into that junction, the current through resistor 1, will have to equal the current we have going out, and that current has to split itself between resistor 2 and going towards resistor 3 and then on to resistors 4 and 5. So our current through resistor 1 was that 0.2927 amps. I2 we know, that is the 0.1189 amps that we already found, plus I3, and after a little bit of subtraction, we can get a value for I3, which turns out to be 0.1738 amps. And we have, again, another one of our values, and just like all the other times, we found either the current or the voltage from our general resistor rules, and then we use V equals IR to find the other one. where we're using V equals IR just for resistor 3. So we want V3, I3, and R3. And I3 we just found, the 0.1738 amps. And R3 is 11 ohms. And that gives us a value for V3 of 1.912 volts. And we have yet another value. So already we've used most of our rules. We haven't really used A yet, but we could, and we will here in a little bit. So again, it's time to start thinking about spending all of the voltage from the battery. So we're going to use Rule B here. And this time, R4 and R5 are the only ones we have left, so we probably want to consider a path through the circuit that goes through one of those. So this orange path through the circuit here. The voltage you get from the battery, you have to spend. So the voltage you get from the battery will be spent at follow the current through that circuit. First you hit resistor 1, then you hit resistor 3, then you hit resistor 4, then resistor 6. So if we add up all of those voltages, we should get the voltage from the battery. So using some numbers, that's 12 volts from the battery. The voltage across resistor 1 was that, oh yeah, that was right, 5.854 volts, plus V3, which we just found, was 1.912 volts, plus V4, our unknown, plus the voltage drop across resistor 6, 2.342 volts. And from this, we can solve for, not I4, we can solve for V4, which turns out to equal 1.892 volts. And just like we have before, we just found the voltage across this resistor, so we can use Ohm's Law just for resistor 4 to find the current through resistor 4. So the voltage across 4 was that 1.892 volts. I4 is our unknown, and resistor 4 has a value of 15 ohms, which gives us I4 equals 0.1261 amps. So now all we have left is resistor 5. There's a few different ways we can think about resistor 5, so I'm just going to make R5 its whole own section over here. We're to the end of the circuit, so things get a little easier towards the end of the circuit. We could use option B, or general rule B. All voltage you get from the battery you must spend. And that would tell us that for a different path through the circuit, similar to the orange path but going through R5 instead of R4, so I'll put it up here in gray. For this gray path through the circuit, the elements on that path are R1, R3, R5, and R6. So if we add up all those voltages, we must get the voltage from the battery. So we could get the voltage across resistor 5 this way. And this could tell us, or would tell us, or actually, so that's one option at least. Another option is, well, you could just use Rule A. Voltage drop is the same in parallel. R4 and R5 are in parallel with each other, so we just know that V4 equals V5, which, as we found before, V4 was 1.892 volts, and that is the voltage drop across resistor 5 as well. So from here, we could use Ohm's Law to find the current through resistor 5. But I'm going to show you a different way. So we could also pull resistor or circuit rule D out of our circuit. Current is conserved at junctions. And this junction right here that I've drawn in black is the one in question. So all of the current going into that junction, coming from resistor 3, has to equal the current going out of that junction. I4 plus I5, because that current has to choose to go through R4 or R5. Plugging in some values here, I3 was 0.1189 amps. I4 was I confused myself. There we go. Sorry, I3 was 0.1738 amps. I4 was 0.1261 amps plus I5, which we do not know. And this could tell us that the current through resistor 5 is 0.046, or let me double check my numbers here. So depending on rounding, but doing it this way, you'd get 0.0477 amps. And then from here, you could use resistor or circuit rule E, Ohm's Law, to find V5. So if you used these rules up here in the first part of the R5 section to find I5, you should get the same number that we got down here, 2 within rounding error. And if you did the current first to find that 0.0477 amps, then you used Ohm's Law to find V5, you should get, 2 within rounding error, that same 1.892 volts back out of that resistor. So do get slightly different numbers because of the rounding error slowly accumulating, even keeping 4 decimal places on all of my currents and 3 decimal places on all of my voltages. So do be careful with rounding error. It won't be such a big deal on the tests, but if you're doing a problem like this on the homework, you will really want to keep a lot of decimal places in your work to avoid the rounding error starting to pile up, because we went through a lot of steps in these calculations. So just to give you an idea, when I used Ohm's Law to find I5, I got a value of 0.0461 amps. So you can see that's very close to the 0.0477 I got using Rule D, but it's not exactly the same, and that's about how much your rounding error can start to pile up even with this many decimal places. The one last thing that I want to tell you guys about this problem, a couple things. One, we used an ideal battery. So if we weren't using an ideal battery, then there would just be a tiny resistor here at the beginning with an internal resistance, lowercase r. But other than that, you'll notice that we kind of worked in reverse order to how we found the equivalent resistance. When we found the equivalent resistance, we started over here with R4 and R5, then added in R3, then R2, then R1 and R6. But when we get to all of this stuff, finding the currents through everything and the voltages across everything, we went the other way. We started at the battery, and then we did 1 and 6 first, then 2, then 3, then 4 and 5. So if you're lost for the order with which you should proceed through the circuit, a general rule that might be helpful is to go in the reverse order that you did for combining the resistors to find the equivalent resistance. This is a rather complicated resistor circuit. Not overwhelmingly complicated, but this problem would take a lot of time. So for the purposes of midterms, I will end up giving you a simpler circuit, but some of the ones on the homework and on the paper homeworks are around this complicated, so it will be good if you can follow all the way through this worked example. And also, if you can start with just the problem statement, just this circuit diagram at the top, and work through it yourself without needing to watch the video, then that means you understand it very well. So, don't have much room here, but I will make myself a little copyright. And I will see you all in class on Friday. Have a good day.